The path of 3i Atlas takes it closest to Jupiter on March 16th, 2026.
For decades, space has followed one rule when objects travel this far. They miss, they drift, or they break apart long before reaching anything precise. But 3i Atlas just broke that pattern in a way that is forcing scientists to slow down and rethink what they're looking at. It crossed into Jupiter's gravitational control zone with a level of accuracy so extreme that it matches what engineers spend years trying to achieve with spacecraft. There were no signs of instability, no visible propulsion, and no random deviations along the way. And that leaves one uncomfortable question sitting at the center of the data. How does something with no guidance system arrive like it had one the entire time? The impossible decimal. When dealing with long-range movement in space, scientists expect a high level of uncertainty. Even the most advanced simulations must account for complex forces like solar gravity, orbital drift, and measurement noise. That's why, for most comets and asteroids, hitting a target even close to a planet's orbit is considered a successful prediction. But 3i Atlas didn't just arrive close to Jupiter's domain. It entered a narrow mathematical corridor with a precision that demands a different kind of explanation. According to data from March 6th, 3i Atlas crossed into Jupiter's Hill sphere with a position margin measured at less than 1 part in 26,000. That means that for every 26,000 possible arrival outcomes, this object hit one that matched an extremely narrow target zone, only about 35,000 miles wide, around a planet that sits nearly 500 million miles from Earth. To grasp how exact this is, picture standing in Los Angeles and throwing a needle across the country with the goal of landing it on the edge of a coin in New York. This level of accuracy is not a rounding error, and it's not a generous coincidence. It is deliberate positioning carried out across hundreds of millions of miles. The Hill sphere is not a place you can see. It's not marked by rings or radiation belts. It is a theoretical boundary defined by the competing pulls of the Sun and Jupiter. Inside this region, Jupiter's gravity takes control of nearby objects. Outside of it, the Sun dominates. Natural bodies that cross into the Hill sphere are often captured or flung away, depending on their speed and angle. Most never make it to the boundary itself with any consistency because the forces at play are dynamic and highly sensitive. What makes the situation more complicated is that the Hill sphere is not fixed. It changes slightly depending on Jupiter's position in its orbit and the combined gravitational influence of nearby bodies. So the fact that 3i Atlas timed its entrance with such tight precision, and did so while maintaining orbital coherence, means that it had to compensate for changes that are not easily predictable unless the object had access to a continuous model of the system. That would require feedback, correction, and a method for adjusting its approach long before arrival. Astrophysicists typically look for signs of internal propulsion or reaction forces when analyzing these kinds of maneuvers, but 3i Atlas has not exhibited any visible outgassing plumes, chemical trail signatures, or momentum loss events. It has simply moved in the correct direction at the correct speed and entered the correct location with the timing of a mission clock. And that raises a difficult question. How does a body from outside the solar system pull off an arrival maneuver that spacecraft engineers would consider challenging? There is a mathematical explanation often discussed when dealing with objects that arrive at balance points in a gravitational system. The concept is called trajectory targeting, and it involves identifying low-energy entry paths into gravity wells. These paths can be found using numerical simulations of orbital mechanics, and they are often used in mission planning to reduce fuel costs. The problem is these paths are not easy to locate without extensive data. They require knowledge of the moving target, the forces at play, and the ability to adjust as those forces shift over time. For a random comet, these conditions don't apply because comets are shaped by heat, outgassing, and unstable cores. They drift, they wobble, and their orbits are distorted by non-gravitational forces. But 3I Atlas has shown none of that instability. It approached in a clean arc, entered a low-energy window, and stopped in a zone that allows for orbital station keeping with minimal acceleration. This is a tactic used in satellite engineering when planners want to maintain a probe's position without wasting fuel. By parking at the edge of a hill sphere, a spacecraft can stay in place with very little effort because the gravitational tug from the star and the planet cancel each other out. But for a natural object to find this exact pocket without aid is like finding a blindfolded exit in a spinning maze. If the numbers continue to match what's being observed, then 3I Atlas is no longer behaving like a visitor from the stars. It is behaving like a system that understands the gravity map of our solar system and is using it on purpose. Thermal survival. When a comet or asteroid travels toward the Sun, it extreme thermal stress because the heat from solar radiation begins to strip away its surface materials and increase pressure inside any frozen core. For most known objects, this results in violent outgassing, surface cracking, or full disintegration, depending on the material strength and internal composition. But 3I Atlas did not follow that pattern. It passed near the Sun, endured solar heating, and emerged more stable than before. This behavior contradicts the model that most astronomers use to describe comets, which treats them as irregular mixtures of dust, ice, and organic material. These so-called dirty snowballs lose mass rapidly under solar heat, and their paths become harder to predict as jets of gas push them off course. But with 3I Atlas, no major shedding event was recorded. There was no visible coma, no fragmentation, and no sign that the object was losing material in the way that fragile bodies typically do. Instead, the signal quality from tracking stations actually improved after perihelion, which suggests that the object's surface or structure became more reflective, not less. This has led to a growing interest in its albedo, which is the measure of how much light an object reflects. A high albedo would mean that the object reflects more sunlight than it absorbs, which would explain its thermal resistance. The more light it reflects, the less energy it has to absorb as heat. The mystery deepens when we compare it to Oumuamua, another interstellar object that entered the solar system with unusual properties. Oumuamua also had a high albedo and showed signs of being metallic or covered in a surface that resisted heating. It too lacked a typical coma, showed no visible outgassing, and performed a small non-gravitational acceleration. These similarities raise the possibility that 3I Atlas might be made of a composite material, possibly a metallic alloy or a hydrogen-based surface, that behaves differently under solar exposure. One theory gaining traction is that the object might have a form of hydrogen ice coating, which would sublimate without leaving visible trails and could create smooth, stable acceleration patterns. Hydrogen ice is hard to detect because it doesn't reflect light in the same way as other materials, and it reacts quickly under heat. If this were the case, it would suggest that 3I Atlas is not just an object built to survive close solar passes, but one designed to use them. Another possibility is that the surface is metallic, with properties closer to aerospace heat shields than to comet crust. If it has layers of fine reflective particles or a structured outer shell, it could manage solar radiation far more efficiently than a natural rocky body. This would also help explain why the object hasn't cracked, splintered, or changed its spin state. While all of this might still fall within extreme natural variance, the combination of features pushes that explanation closer to the edge. It is rare for an object to enter the inner solar system, survive solar heating, make a controlled correction, and then stabilize in a complex gravitational region without shedding mass or altering shape. This has forced researchers to begin treating 3I Atlas less as a comet and more as a case study in thermal resilience. And that means evaluating its behavior not as an outcome of chance, but as a response to predictable energy conditions. Because if the object anticipated solar heat, if it responded to it with stable movement, and if it is now in a position of advantage after surviving it, then someone or something understood those conditions in advance And that would change what kind of object we believe we're watching. The three-body headache. One of the hardest problems in physics is understanding how three large objects affect each other's movement over time, because once more than two forces are involved, the math becomes chaotic. This is called the restricted three-body problem, and it describes how a small object moves when caught between the gravitational pull of two much larger ones. In this case, the two large forces are the Sun and Jupiter, and the small object is 3-1 Atlas. When a body enters this kind of system, its motion becomes unpredictable unless it has either perfect timing or some way to adjust in real time. The gravitational pull from the Sun is strong, but Jupiter also exerts massive influence across its surroundings, and this means that objects caught between them don't follow stable paths unless every detail of their position, speed, and angle is exactly right. For a spacecraft, this kind of control requires constant calculation and very careful course correction. For a natural object, it should lead to instability. But 3I Atlas has not shown that instability. Instead, it has remained steady while crossing into a region where the math should fall apart. Scientists noticed this because of something that happened shortly after its closest approach to the Sun. As the object moved away from the solar heat, it did not follow a clean curve shaped only by gravity. It accelerated slightly, in a direction and with a timing that did not match what gravity alone would cause. This event was labeled non-gravitational acceleration, and while that term sounds technical, it really means the object changed speed or direction without any outside force like gravity pushing it. The most common explanation for this behavior in comets is outgassing, which is what happens when frozen material inside the object heats up and escapes, causing the body to shift slightly in reaction. But outgassing is messy, and it usually causes wobble or tumble, because the gas jets don't always fire in even directions. What 3I Atlas did, however, was more precise. Its course changed in a smooth, calculated way, and there was no sign of spin or loss of balance. Its motion didn't match the uneven shifts we usually see from jets of gas escaping. Instead, it looked like a maneuver, and not just a random push. The absence of visible gas trails, changes in brightness, or rotational irregularities makes it hard to defend the standard comet explanation. If the change had been caused by natural forces, then at least some side effects should have appeared in the data. Instead, the movement was clean, centered, and quickly stabilized. That kind of behavior requires damping mechanisms or internal correction, which are only known to exist in engineered systems. It's also important to note that this happened while the object was transitioning into Jupiter's gravitational influence. Timing any course correction at that moment would be extremely complex, because even a small mistake would send the object out of range or trap it in a high-speed slingshot around the planet. Yet the object slowed down, adjusted, and entered the Hill-sphere corridor in a way that avoided capture or escape. The entire approach suggested not just knowledge of where Jupiter would be, but how to enter a balanced zone between its pull and the Sun's. That level of precision matches what we've seen in deep space missions designed to enter orbit around Lagrange points, which are similar balance zones in other gravitational systems. But those missions require teams of engineers, constant tracking, and fine-tuned propulsion. 3I Atlas had none of those tools, or at least none that we can detect, which means either it's hiding its mechanisms extremely well, or it's using a form of control we haven't yet understood. In either case, it is moving through one of the most unstable regions in orbital physics, with total confidence. And that's why scientists are uncomfortable, because the data shows more than coincidence. It shows something navigating an environment that should be impossible to survive without a plan. The Jupiter Gateway. Jupiter is more than just the largest planet in the solar system. Its massive gravitational pull acts like a switchboard for space traffic. It bends the paths of comets, captures rogue asteroids, and sends spacecraft into new orbits with almost no fuel cost. Because of this, any object that approaches the planet is usually studied very closely, not just for its origin, but for its trajectory. The way an object behaves near Jupiter tells us a lot about whether it's being controlled or just drifting. This idea is supported by a known theoretical model called the von Neumann probe, named after mathematician John von Neumann. This model describes an autonomous machine that travels between star systems, harvesting energy and materials while performing tasks like mapping, monitoring, or seeding smaller systems. A von Neumann probe doesn't need to be fast. It just needs to be able to stop, refuel, and replicate or release smaller payloads once it finds a stable environment. And it doesn't need to look like a machine, it only needs to function like one. 3I Atlas is now located at the very edge of Jupiter's Hill sphere, the invisible boundary where the planet's gravitational pull becomes strong enough to dominate over the Sun's. This region is not commonly used by natural objects because it's difficult to reach and hard to stay inside without being pulled further in or thrown outward. But for a spacecraft or any system trying to use Jupiter as a launch point, this location is valuable. It offers a path into almost any part of the solar system with very little added energy. This is why mission planners often use Jupiter for gravity assists, which are maneuvers that let a probe gain speed by borrowing momentum from a larger body. NASA has used this method many times, including for Voyager, Galileo, and New Horizons. By swinging around Jupiter in the right direction at the right time, these missions saved fuel and gained speed to reach their final destinations. But gravity assists require timing, coordination, and exact positioning, and they only work if the object approaches from the correct angle. 3I Atlas is not swinging past. It is slowing down, and it has stopped at a position that gives it access to all possible launch paths. From where it currently sits, it can go deeper into the outer solar system, dive toward the Sun, or change direction and begin moving toward the inner planets, including Earth. What makes this possible is the low energy cost of movement at this location. Because the gravitational forces from Jupiter and the Sun nearly cancel out, it takes very little push to go anywhere. This spot is the ultimate junction, and now something is sitting right on it. Scientists watching this movement are preparing for several possible outcomes because the object is positioned in a way that suggests future change. The first scenario is that tidal forces from Jupiter will eventually overcome whatever structural integrity the object has and pull it apart. This would create a cloud of debris, similar to what has been seen with other comets passing close to gas giants. If this happens, the pieces would spread out across the Jovian system and become part of the natural background of captured objects. The second scenario is that the object uses the Hill sphere as a springboard, performing a new acceleration that launches it toward the inner solar system. If this occurs, it would require a controlled burst of energy because the current velocity and angle are stable. Any change from this point forward would need a clear force to make it happen, and that's why scientists are watching so closely. If the object shifts direction deliberately, it would prove that it is not just passive. The third and most concerning scenario is the deployment model, which suggests that the object may contain smaller bodies or instruments designed to be released while the main mass remains stationary. In this scenario, 3I Atlas is not a single object, it is a carrier. Its current position would make it the perfect launch site for dozens or even hundreds of tiny probes that could be released into the Jovian system or beyond. These probes would need almost no fuel to move, because the gravitational balance here would do most of the work for them. This theory is often dismissed because it requires a level of design and purpose. But the behavior of 3I Atlas so far already points towards something more complex than a random rock. It made a stable course correction, it survived a close solar pass, it stopped in a mathematically precise pocket of gravitational calm, and now it's holding position in a way that gives it full reach across the solar system. In mission design, this kind of positioning is intentional. In nature, it is almost never seen. A mission, not a mystery. The arrival of 3I Atlas has forced the scientific community to look closer at something they were never prepared to explain through math alone. Over the course of months, this object has moved through our solar system with a precision that has broken pattern after pattern, leaving behind data that resists random explanation. It approached the Sun without destabilizing. It passed through thermal stress without losing cohesion. It performed a course correction without tumbling. And now it has stopped at one of the few locations in space that allows for complete gravitational leverage with almost no energy use. There is no known comet or asteroid that can survive all these phases with such consistency. And there is no known natural object that uses three-body dynamics to navigate into a parking slot that mission designers spend years calculating. Every major system in astronomy has been applied to 3Y Atlas, and none of those systems can explain how a supposed comet has avoided every known failure mode. The absence of debris, the smoothness of its corrections, the apparent resistance to sunlight, and the careful selection of its current position are all facts that remain in the data, and none of them have been dismissed. If this is not random, then it was calculated. And that means something chose to send it here. The object is still in position. It is still being tracked. And every hour it holds this location. A position where natural objects should destabilize adds weight to a single conclusion. This arrival was not random. It was calculated.